My name is Ryan Sr. I work for Revelytics in St. Louis, Missouri. I've been doing writing closure code full-time for about 2 years now. I'm also a co-organizer of Strangeloop, so that'll be pretty exciting. More information will be coming out about that soon. My contact information is up here. Does everybody here at least know what core logic is? Is there some people that? Okay, so it's basically logic programming for closure. So it's based on Minicanron, which is a scheme implementation of a logic programming system. David Nolan ported that over to Clojure, and so what this talk aims to do is give you the tools to get up and running with core logic with minimal theory, without having to go through a bunch of books. So it's definitely a good use of time. The Reason Schemer is a great resource. Art of Prolog is another one. And there's an ocean of great logic programming documentation and research out there. And it can be kind of daunting, actually. So, my goal of this talk is to get you far enough that you can do something useful with it, like today, like when you leave here. So there won't be any zebras, and we're gonna start from nothing. So if you're not familiar with the zebra problem, it's a logic programming problem. A lot of people use it as an example of what you can do with logic programming. But I'm gonna keep a focus on the practical here. So why would you do logic programming, or why would you use core logic? And I believe that some problems are just easier with logic programming. I don't think that is the solution for all problems, but I think there are certain problems that are very well suited for logic programming, and having something like that available to you in Clojure is a much lower cost of entry, right? So if I wanted to solve a problem using Prolog, I'd have a lot more explaining to do to my boss than adding another jar, right? So and what I'm going to specifically focus on in this talk is some code that I had written in Clojure for querying a graph, and I'd written it in straight Clojure, and I felt that the solution was very unwieldy, and I dropped core logic in it, and I have a much cleaner, much more robust solution. And so what I'll do with this talk is I'll start from that use case, and I'll kind of give you a good reason why you would use core logic based on my use case, explain what I was trying to solve when I wrote it with plain Clojure, and then what the solution looked like in core logic. So to know how I applied, to know what I'm doing with it, first I feel like I needed to explain a little bit of the project that I work on. So I work on a product called Spinner at Revelytics, and it's a query federation engine, a Sparkle query federation engine. And if you're not familiar with Sparkle is like SQL for RDF data. So you issue a SQL-looking sort of query. It goes to a Sparkle endpoint. Sparkle's both a protocol, like a HTTP-based protocol, and like a query language like SQL. And so it will then give you tuples as results, kind of like you would with SQL. And so the federation engine aspect of it is you issue one query to the federation engine, and it could pull data back from many sources to give you one answer. So kind of the drawing I have here is a Spinner instance has two federation instances out the top, so 2 points in which you can query. And when you issue a query to one of those federation instances, it may pull data from one source, 2 sources, 3 sources, however many is needed to give you the results of that query. And so where core logic was fitting into the mix was in order to configure this, we use the W3C service description spec. And so service description is currently in draft, but you can kind of think of it as a WSDL-like thing for Sparkle endpoints. And so it's not as rigid as WSDL. It's meant to be extended. It's meant to be more flexible, and there's not tools around it or anything like that. But the premise is the same. You create a service description, and it has information in it, like what kind of graphs are contained in this Sparkle endpoint, what's the endpoint, like what's the URL that I use to connect to it, what versions of the Sparkle language this endpoint supports, and So in Federator and Spinner, we use this at many levels. So the Spinner, a Federation instance in Spinner is itself a service. So that's one service description. And inside that, you could have many source services, right? So you could have your relational database that you're wrapping in a Sparkle endpoint, and then you could have like a publicly available Sparkle endpoint like DBpedia. And so we have the top level service description, and then we have the service description around our service, our source service. So you can download a service description from DBpedia if they had one, and you would wrap it in a service description for Spinner. So that would say like how you want to alias this service, what kind of query timeouts you want to allow for this service. And so what we have is basically like a hierarchy of these service descriptions, things that kind of look similar but have pertinent information that I need at every level. All of these things are defined in RDF. So a service description is an RDF ontology. And RDF is, which we've heard several times at the Conj or at the Closure West already, it's a resource description framework, and it's a subject predicate object, which means everything is described in triples. So person, first name Ryan, person, last name Senior. It's always in threes. And but how that is represented is separate, the serialization mechanism. And so what I've got here is a service description. It's just from the W3C site. You can see it's got the things we've been talking about. Something is a service, so that's is of type service. They got the endpoint URL, what languages it supports, what result formats it supports. Now this is the turtle serialization of the W3C service specification. And so the problem is, and like I said briefly earlier, is that RDF is very flat. It's all triples, right? There's only threes, even though what we're modeling is very hierarchical and very nested. And so the problem was making a flat thing hierarchical via closure code was cumbersome. And so this is an example of like a snippet of a Spinner config that's got the three levels that I was talking about. So you got the Federation service at the top where we've got an alias that we call a name, and it exposes these services where you see SDX service collection, service A2, service A3, service A9. And then down below that, you got A2 as a federated service, right? So this is what's going to wrap a DBpedia thing, or in this case, it's IMDb. And then below that is A4, which is a service. This would be the kind of thing that you would get from, you know, a fictional IMDb website or DBpedia or something of that nature. So if you take away the turtle syntax, so before A1 is only listed once, and then below that, name, movies, and expose the service, that thing over there, those are twos. That's really just syntax sugar. When it's kind of expanded out, everything's always threes. So A1 of type Federation service, A1 name, movies, A1 expose the service, service collection. So that maps pretty easily into something closure-y, right? So a graph is, we can think of that as a set. And a triple is just a vector where the first item is the subject, the second item is the predicate or the property, and the third item is the object. And so this is how we've got an internal RDF library, and this is how we, kind of a primitive way that we represented RDF. So the gymnastics that you have to go through to process this thing is pretty crazy. So you got a graph sitting in front of you, and you want to find the Federation service. In particular, you want to find the subject of the Federation service. So that's the top left of the screen there, so A1. Once you found that, you need to find the services that A1 exposes. So you drop down 2 lines below, and you find the service collection. And you do the same thing to get from the service collection down to the federated service. And then you keep following all the way down to service. And this is a specific example. There are other examples, even within a particular service, like trying to figure out all the graphs that's exposed in that service. It's all very very imperative. So I'll kind of outline a little bit of the closure solution that we had. So the first function here is just match. It's just given a triple pattern, and this one given like a specific triple, and then given like a subject to match it with, whether or not we've got a match. So We got wildcards that always match. We got a specific subject that we're looking for that will match only on specific triples. And then below is just kind of a basic filter. So given a graph, go through that graph and find a triple pattern that matches this template. And so here's kind of how it's used. With the thread macro here, I've got a graph, passed into GIS statements. I'm looking for something RDF type federation service. So this is the A1 guy that we were looking at before. And so that's going to return a list. Filter returns a list, right? So it's going to return a list of matches that are federation services. And so in my case, I only care about the first one, and I only want the subject, so it's going to return me a vector. All I want is the first item of that vector. So obviously this guy needs to be wrapped in a function, and so I did something like that. And that only gets me one step of the way, right? So I write something else that gets me from the federation service down to a service collection, the things that it exposes. And so I bundle that up in a function. And then I need to find the many services that this particular thing exposes. And so right about this time, I've got a lot of these things piled up, and the structure of my data, what I'm actually looking for, is so obscured by these piles of functions that I'm now having to kind of fit together that I felt like the code was really getting unwieldy. And so I looked at using CoreLogic to see how it could help me with this. And this is exactly equivalent to the last 4 slides or whatever that we saw. And you can see here that it still has the shape of the data that I'm looking for. The query is embedded directly in there, and I no longer have to remember what all these individual functions do, right? So I've got a variable here, $A. I don't care what that is, but whatever that guy is going to expose some services, $B. And I don't care what $B is either, but what I do care about is the service that's the last line on the right side. And so in CoreLogic, Q here is what's actually going to end up being returned, and so it's easy for me to just slot that in. It also scales better. So as I just had a very small example of going from a federation service just down to the federated service below it, but there's a lot of those levels that I needed to go down, and so having to create new functions and massage those together for every new thing, like I said, it ended up being unwieldy. So here, I've now gone down another level in that graph, and I really only added a few lines, and we still haven't lost the essence of what we were looking for. So from here, I'm going to cover a little bit of CoreLogic fundamentals, and what we'll do from there is start from just the basic CoreLogic functions and macros, and we'll build up to be able to do what Gmatch that I created does. So all of your CoreLogic programs run inside of the run macro, and so it should be your cue that you're entering a different world. Okay, the way that this executes is different. It's unification, not evaluation. So you can't put just regular closure code that's unaware of CoreLogic in the middle of a run statement and expect it to work. You also need to tell CoreLogic is going to be solving your puzzle for you, and so you need to tell it how many solutions to this puzzle that you want to see. It's possible to have infinite solutions to CoreLogic puzzles, and so you need to tell it that you only want 10, otherwise you're going to be waiting quite a long time, right? And Q, here in the brackets in the middle, it always has your result. That's like your output variable. So next most important thing is unification. Everything in CoreLogic, all values are always determined via unification, and that's the equals equals. Order doesn't matter. You can unify before, during, after you use some of these logic variables, and CoreLogic will be able to figure it out. The only case where order does matter is if you're doing recursive calls. Ordering of recursive calls can be a little tricky, but other than that, it doesn't matter. So what equals equals xy means, whenever we see x, we actually mean y. And unification is deeper than just a particular X and Y. You can have lists, you can have strings, you can go, here we've got a variable X that's actually inside a vector, and it knows how to unify that, no problem. So this is always a question. I think it came up on the mailing list recently. What's with the O? I mean, really, guys, come on. So it comes from the reason schemer, and it's kind of unfortunate that it doesn't translate quite as well in real code. But in the reason schemer, it's actually a superscript O, and I think of it as like a visual cue that there is something different about this function. And so this function is not something that you can just go and take and run anywhere. It's meant to be run inside of run star. And so when I see the O on the end of the function or macro, I just take it as a visual cue, just like swap bang, right? When you see a bang at the end of a function call, that's a cue that says there's going to be a side effecty thing going on inside this. There's going to be a relational thing going on inside this. So special. So I've alluded to logic variables several times. What a logical variable is it's a bucket. You create it, CoreLogic fills it. Okay? It's going to fill it with what it needs to solve your puzzle. And values are always determined via unification. And I already snuck a logic variable in on you. That's what Q is. Right? You guys didn't even know it. You create new buckets with fresh. It is possible to create new buckets via like direct calls to a function called lvar. I would say that's less common. Usually what you'll want to do is fresh, and fresh is what we'll be doing in live coding that we'll do here in a minute. And the other thing that can be kind of tricky is that logic variables can be anything, or they can be nothing. If at no point do they unify with something and they're simply unbound, the way that CoreLogic tells you that is when it reifies, it will swap the lvar, that var1, var2, whatever you called it, with this underscore dot number notation. And that signifies a specific logic variable does not have a value, was not unified. The last thing that I'll mention here is lists. This last thing that we'll need to kind of bootstrap our CoreLogic. And so lists are slightly different in CoreLogic because of the possibility that the tail of your list is a logic variable. And so lists in CoreLogic called lcons, and it's really pretty simple. It's just a def type. A is first, D is rest. You can ignore cache and metadata for right now. And if D is a collection or it's nil, then it goes ahead and just creates a normal, regular cons for you. Otherwise, it creates this lcons def type. All right. So from here, we'll get into some actual code. And like I said, we're going to, using just these fresh, some logic variables, lcons, and unification, we'll build up something that we can do this graph querying with. So we'll start out with kind of the most basic puzzle that we can give CoreLogic, and here we're just saying unify Q and 1. I mean, obviously this is pretty basic. The answer is going to be 1. So how I'm going to do this is eval some code. We'll see it, talk about it, and we'll move on. All inside the buffer here. So as I mentioned, with the O notation, there's something special about these functions. You can't just run the function wherever you want and get something meaningful back. Right? Exception. It's you also can't just drop regular closure code inside your run clause and expect it to do anything useful. Right? So class cast exception, long cannot be cast to a function. So run star is meant for running goals, and +1 is not a goal, right? If you write that, you're expecting it to be evaluated, and actually CoreLogic needs to unify it, so it needs goals. Also, unification is not assignment. So even though you and I look at this and we say, well, Q has to be 1. Right? That's the only way that's going to be able to solve this puzzle. Well, this is going to break too, because you cannot increment a logic variable, right? L(var) cannot be cast a number, right? Because Q is not a logic variable, or Q is not a number. Q is a logic variable. So I mention these things because if you're like me, first thing I tried on core logic was, equals Q1 or whatever, and the second thing I tried was this, and of course it failed miserably, and I had no idea what was going on. So from there we'll get to failure in a different way. So here we're giving core logic a problem it can't possibly solve, right? So we're saying that Q is both 1 and 2 at the same time. Now this isn't an exception. This is a failure. So core logic can't find you a solution to this problem. It is not able to unify this and have Q be both values. So no answer. There's no solution to this. And now run star always returns you a list of solutions. If there's one solution, it'll be a list that has one thing in it. If there's 10 solutions, a list with 10 things in it. It's always a list. You can also unify any kind of thing. You can unify lists, you can unify strings, you can unify integers. It's not picky. And so here we just did the exact same code, and only instead of 1, we've got a string called foo. Get a little higher up. So here, something a little more complex, but it's still the exact same. It doesn't care about type. So here is something a little more complex, at least on the surface. Here we wanted to unify 1 in Q with 1 in foo. Right? And the only way for core logic to solve that problem is if Q is foo. So far we've been looking at goals, but lcons is actually not a goal. This is just a plain closure function that we can run and get a result back outside of a run, inside of a run, wherever. Now, one of the things about core logic that can kind of seem a little off to closure people is that some of the conventions used in core logic map more to scheme and to mini-canron, where it comes from. And so this dot notation is one of them. This stumped me for a little while when I was reading Reason Schemer, trying to understand what this dotted notation is. And I think of it as kind of like a cons, but could have an improper tail. So here we got 1 dot some L(var), and so that's just shorthand for first dot maybe something, because it could have an improper tail. And like we saw on the slide before, if you hand lcons a proper list for the rest argument, it will do the right thing, return you a regular list. So what we'll do from here is we'll recreate some core logic functions, some functions that are already in core logic that but we'll recreate them ourselves so we can kind of get an understanding of what they do, and we'll build off of them. So Conzo, and Reason Schemer called Conzo the Magnificent, it's going to unify list L with lcons of first and rest. So again, equals is a goal, so we're creating a new goal. And it's very common to have an output variable. In this case, the output variable is L. And we take these two things, and where we would normally return it, like in cons, instead we unify it with this output variable. And this also allows us to roll it backwards, right? Go backwards, go forwards, and we're going to use that implicitly here with our new function Conzo. So here we got two functions, or two new snippets of code. And so we use q as the output variable. So this would be using it like you would a normal cons. So we're saying cons 1, 2, 3, 4, and put it in the output variable q. Again, q is always what's returned by CoreLogic. So anything you unify into q is what you're going to get back. And so here we're going to, it's not anything too different, but we're going to start getting into something a little more complex. All right, so here we got, instead of changing the output variable, we're going to set the output variable. Okay, so here we're declaring that the list, when we're done with it, whenever it's done doing what it's doing, is going to be 1, 2, 3, 4. And the rest of that list is 2, 3, 4. So q is obviously got to be 1, right? So here we're now we now got q in the middle of the list. So we're saying glue together 1, 2, something 4, and the resultant list is going to be 1, 2, 3, 4. Again, unification is going to figure out the right steps for us to solve our problem. So it doesn't matter whether our variables and what we're looking for is the first, the rest, or something in the rest, or something that's in the output. So again, this my first O, he's also in CoreLogic already, but this is something that's a little different. We're saying, give me this list and bind the first item to this output variable. And so to do that, we're basically doing a cons with a fresh variable for rest. So first item goes in f. That's easy. That's our output variable. And we're creating a new logic variable, r, and we're saying we don't care what the value of that is. So it's going to, CoreLogic is going to do whatever it needs to do to position f to be the first, slot everything else as rest, and then L is the list that we actually passed in. So with that, we can do the same thing that we've been doing previously. We can give it a list, 1, 2, 3, 4, 5. My first though, and we can declare that q is the first item of that list, and obviously we'll see that it's 1. Now here we'll get a little more fancy. We'll create a new variable, myList, and we'll say that q is the first item of that list. Now note here that we haven't unified myList with anything. Again, I said order doesn't matter, right? So we can put this unification after, we can put it before. CoreLogic's going to know how to do it. So we say myList is actually some string here, and like we would expect, q is going to be, there's only one result, it's going to be some. Rest is defined the same way, not much different. So now we get into something a little more interesting, and this is cond-e. Cond-e allows so far what we've seen, there could only be one answer, right? We unified a logic variable with a specific thing, a list, an item in a list, a string, an integer, but there only was ever one answer. Cond-e lets you have more than one answer. And so cond has syntax kind of like, cond-e has syntax kind of like cond, but the E says every line. That means every line gets a chance to succeed and to run. So in a particular cond-e clause, the first item is the test. So something that is going to be successful or is going to fail. And the rest of the cond-e line is going to be ran pending the first thing succeeding. So I kind of glossed over the idea of failing and succeeding because a lot of it's implicit. So when q unifies with 1, and that can happen, right? So like the example that we had where q was both 1 and 2, the first unification succeeds, the second unification failed. And so that's less interesting unless you're in the scope of a con like we are here. So here, we're automatically saying that every test clause in this con D succeeds. So in this case, if core logic is saying that 1 is a perfectly valid answer, 2 is a perfectly valid answer, or a vector of 1, 2, 3 is a perfectly valid answer. And so when a variable like q, in this case, q is fresh, going into the con D clause, it gets unified in the con D clause, but once it exits and goes to the next line in con D, it's as if that unification never happened. So, which is a very powerful tool. It allows you to just declare things so. And if it works out, great, it's a solution. If it doesn't work out, it goes to the next thing. And we're going to lean on that pretty heavily. So here, we've got a similar example, but with one guy that fails in the middle. So this guy succeeds, and we unify 1 with q. This guy fails, but we're going to try to unify q and 2, and then the last guy is also going to succeed. So here, since the middle line fails, the test condition fails, q doesn't get bound to 2, so that's not an acceptable answer here. Another thing I didn't mention is I'm using parens to wrap the con D clauses, which is a bit foreign for us closure guys. I think it also supports brackets, kind of a little more closure-y, but parens is what they use in the reason schema, and so if you're trying to go based on that, you want to use something kind of like this. So the next example has a similar result, but gets about it in a different way. So here, we have the second clause in con D is the same, but the third succeeds. The test condition succeeds, but fails in the body of the clause. So in here, we got our good friend Q getting double unified again. In this case, only the first guy succeeds. So again, con D, very much we're leaning on the fact that if it's successful, we use it. If it's not, don't freak out. We'll get it later. So using this, using these pieces, we can make something that's a lot more useful. And this is my membro. Membro is a function that's in core logic, implemented slightly differently, and we'll move to its implementation shortly. But this is an example of something that doesn't necessarily have an output variable. This is kind of more declarative, predicate style. X is a member of this list. That's what we're saying. And so we're using con D and its ability to succeed or fail at every line to be able to declaratively say that this item is in this list. So we're using our good friend myFirsto here, and we're saying that we're declaring X is the first item in this list. So if that's true, we know it's a member and we're good. So what about the case when it's not the first item in that list? Well, we get down in here to the second clause. We create a new fresh variable called the rest. We use our function myResto here. So it's going to take a list, get rid of the first item, give you the rest, bind it to this logic variable, the rest. Now it's going to declare X is in the rest. Right? So using this, we can now have some fun with matching in a list. So here, I'm declaring that 20 is in this list. Right? So we got a list 1, Q, 2, 3. So when we go into this, it's going, again, we've declared that 20 is in this list. 20 doesn't appear in this list, but Q does. And so core logic is able to finagle things in such a way that, well, if I make Q 20, then this will succeed, and this will be a successful answer. So it will set that. And then the next one is maybe a little less interesting, but here we've declared that some fresh logic variable, Q, is in this list. So it is the list itself, right? So it's perfectly valid that 1 is in that list, or 2 is in that list, or 3 is in that list. So we have 3 possible solutions to this query. This is a sugared syntax for what we just saw. This uses the match E macro. The result of this is the exact same. It's just kind of some shorthand. So what's going on here is, and there's also an even shorter hand where it takes the declaration of the function and it treats the body as a match clause, but I'm not going to have any examples of that in here. So match E takes a list that we're going to match on, and then condy like clauses, and then within that we've got these 2 sets of brackets, and it can, since I only have one list here, it kind of looks funny, but if we had L2 and L3 here, you could do other things. So the paren is for grouping the matchy clause, kind of like a condy clause. The outer bracket is for grouping your arguments, right? All the things that you're matching on. And then within that, you are matching against this list. And so in this case, I'm matching a list, and I'm declaring that the first item in the list is X. And here's our dotted notation again. So dot, whatever else, I don't care. Underscore, it doesn't matter. But this X is the same X that I'm passing in above. So I'm declaring that this X up here is the first item here. And when that fails, I'm creating a new logic variable. So R here, it's going to create it for me automatically. And then I'm going to just recursively call, say, again, my member X is in R. So with this, we can do something a little more interesting. So here, I'm not actually declaring that X is a list. So here I'm saying that 2 is a member of X, 10 is a member, or sorry, 2 is a member of Q, 10 is a member of Q, and the first item of Q is this keyword first, right? So it gives you, I asked for 5 solutions, it gives you 5 solutions that satisfy this. So the first one, obviously all of them have first as the keyword, first thing in the list. And so the easiest one is, okay, well I got 2 and then I got 10. Well, what if I got 2 and then some other thing and then 10? What if I have 10 and then 2? And so it will give you infinite answers. Unfortunately, I don't have enough time to show you infinite answers for this, but you'll have to trust me. So that's kind of interesting because it shows how CoreLogic has inferred that you want this to be a list based on the things that we've told it, and based on using different variables in different ways. It doesn't necessarily matter that we're going one way or we're going the other. We're getting it done. So here I'm creating a example graph, kind of like what we saw before, where we got subject, predicate, object, right? We got A1 is a type federation service. A1 exposes services. A2 is a service collection. And so I just kind of built up an example here so that we have something to work with. So this is basically the G match that I used before is basically just syntax sugar around this. So here I'm declaring I've got a bunch of new logic variables here, but that A is a type federation service. I'm looking for it in my graph. This is the thing I just defined. A exposes services B, B is service C. And again, this is exactly the shape that I'm looking for, and I don't have to go hunt through a bunch of functions and different levels to be able to figure out what it is the thing I'm looking for looks like. So here, this is actually more complex than the examples that I gave before, but I'm asking it what are the endpoint URLs that are in this graph. And so it's starting at the federation service, finding all of the federated services, finding all the services under those federated services, and then giving you the endpoint URL at the end. So definitely much more declarative, much more easy to reason about, especially if, like, I got basically what my gmatch macro did is it looked for question mark foo and made a fresh logic variable for you, so that I kind of skipped that first step and then just lets you put the vectors directly in as opposed to putting it in memrow. So if this has an added benefit that, as I mentioned, Spinner is itself a Sparkle endpoint and is itself needs to describe the Sparkle services that it provides. So not only does it parse and consume these service descriptions, but it also needs to have a service description that it exposes out the top. Well, the nice things about kind of rigidly defining the structure of my graph like I have is that I can reverse it, right? So if I take the code that we just had, and let's say I refactor it into a function and I call it endpointo, again, we got to have the O on the end, right? Create a new guy for that. Let's verify that we get the same answer. Right, that's the same answer. I can now take that same thing and generate a service description that is exactly what I just queried, right? And so what's interesting about this is that this underscore dot 0 underscore dot 1 sort of thing, this actually maps very well to blank nodes in RDF. Blank nodes in RDF means that it's an anonymous node that is unique within this graph. And so I can swap these underscore dot 0 for a new blank node, and this can be my service description out the top. And so I'm making this guy pull double duty, and I didn't have to write any more code to do it. So last thing here is another infinite problem. So here, by the way, I didn't explain this very well. I should have. Before, when we called endpointo, we specified the graph, and it gave us the endpoint URLs. Here, we're providing it the endpoint URL, but not specifying the graph, and that's what it generates. So here, we can ask it to generate many graphs, which, although kind of cool, not incredibly useful. So it actually, when I was at the Conj and saw the great presentation by Will Bird and Dan Friedman, and they were running theirs backwards, this is what I was thinking about. That it seemed kind of cool, but I wondered how it could be used, how it could be practical. But when I thought about it, this is exactly what I wanted and exactly what I need to do. We actually don't do this in our product now, but we will need to soon, and so I'll be able to leverage the stuff that I have. So with that, I have some time left for questions or other discussion or other examples. I hope what you guys took away from this is that when your barrier to entry for logic programming is low, such as you can just add a jar to your class path, it can make certain problems easier that wouldn't have been an option. So this is a small win for me. This was very small graphs. It's just config. We're talking hundreds of triples at the most. But the code that I had written and the amount of time I had to put into that was pretty significant. And I spent a lot of time trying to make it look good so that at least I felt like I did my duty as a programmer and didn't leave some poor soul with the pile of code that I left. So if the only option there was to drop Prolog in to straighten or to make my code look good, I couldn't justify that, right? I mean, I'm parsing a triples file with a couple hundred things in it, and yeah, I'm going to bring in another language, Prolog, and that's going to help me out. I wouldn't be able to justify that. But just another jar, that's something I could justify. So. Anybody got any questions?
Yeah, so as you get bigger data sets, how does the performance compare to using this versus
So this is slower. I did some basic basic tests on data sets much larger than what I was going to need, and it was slower. However, what I would probably do is, because our existing graph library has some indexing and things like that, I would probably use that to kind of narrow the graph before I did my matching here. But to be honest with you, my data sets are so small, and the clarity of the solution is so much better. I think it's well worth performance penalty in my case. But you're right, it is slower.
What is the E suffix indicate?
For Condi, it means every line, and it's important because there's a lot of different cons. There's several different cons. E is every line, means every line has a chance to execute. There's also conde and condu and condi, and there's a lot of cons. Yep.
Did you ever find that you needed to understand or keep in mind the search algorithm that CoreLogic is using in order to write your queries or make them performant?
No. And I think that's one of the tantalizing things of CoreLogic is that how it's implemented is so interesting that it begs to be understood as you're trying to do something. However, I think that you can use it without knowing a lot about internals, and I think that that's what I try to do with this approach is show you that you can use it without having a deep understanding of what it's doing. Yep.
This approach seems amenable to like XML config files as well. I would imagine that you ever tried it for that.
No, I haven't. But yeah, I would be interesting to see how it would go. It would be a little more difficult to put it in the list format, as opposed to a flat set of triples. If it's more hierarchical, it'd be a little tough to put it in the list format. Anything else?
So what happens if you have contradicting clauses in the condi? Q equals 1, not equals 1.
So you say what kind of clause?
Like the clauses contradict each other?
Well, it just fails, right? So yeah, so it fails, and actually I think I had an example of that. Yeah, so this is an example of that, right, where Q it's conflicting, right? So the last value says Q is both foo and 1, 2, 3, and it just fails. So you don't get a valid answer for that line.
If you had fail Q1 as second clause, it would be nothing left.
Fail Q1 is you mean like this? Yeah, it would never actually execute that. So. Yes. So there are a couple of functions out there, trace lvars and trace lvar, and there's like a logging goal that I found very useful to try to figure out where the sprockets sprung off, right? Because it's pretty easy to entangle yourself with it, and so. Definitely trace lvars is the way to go. So I found the reason schemer good. I also found the art of Prolog good. I don't know. So I think it's something with logic programming material and documentation that you have to read like at least twice to understand it. And so it's definitely a decent amount of work. And but Art of Prolog I found is really good. Reason Schema is really good. There's also a couple of tutorials and blogs and things that have been coming out. There's a new wiki page, I think, for CoreLogic just recently that also talks about it. One more question, and then maybe you can catch me after. Did you have your?
I was just going to mention the notification just came out.
Yeah. Yep. Thank you.